We will now go through the answers here one by one. Okay. First of all, we have these two units, the astronomical unit and the light year. You need to define each unit. So what is the astronomical unit?
Astronomical unit. Astronomical unit. Okay, isn't that the length from the Earth to the Sun?
Yes, but you have to state it in a slightly better manner. Well, what's the slightly better manner here? Just remember that distance varies. There's a minimum and a maximum value, right? No other possible answer here. Okay, next, so we have an image here of a comet. Comets developed a tail as they approach the sun. Identify one other characteristic of comets.
I don't know anything about comets.
Oh, okay. Okay, so what do we know about comets? Okay, let's just note them all here. Okay, comets are bodies, small icy bodies. They're not rocky, they're icy. Okay, so that's one. Another characteristic of comets is, I think I'll put an image here. Comet orbit diagram. Okay, I'll just show you this in Google. This is a good one. Okay, so the idea here for comets is that when it goes around the sun, okay,
they orbit the sun in an elliptical manner.
That's correct. So that's another possible here. Orbit extremely elliptical orbits. Okay. That's one. That's two. And another characteristic, it's about the tail. Yeah. If you look at the tails always point away from the sun. Okay.
Okay. Tail points away from the sun. Is there a reason or just?
It's about the. You remember when we were talking about solar radiation pressure?
Yeah.
Okay, it's similar to that, but tail always points away from the sun. Okay, the reason here is it's a bit of that. It's a bit of radiation pressure, but mostly it's about what's called solar wind. Okay, basically the sun is projecting all these particles in a manner similar to wind. And that wind is always pointed away from the sun. Because of that wind, and this wind is very similar to how we understand wind here on Earth. Okay? So that sun is producing wind, and the wind is blowing, so to speak, onto the comet. So anything that can be blown away gets blown away. Okay? So that's the idea behind solar wind. Okay, so I think either one of these would be a good enough answer for a single mark. Okay?
Yeah.
Alright, next. Identify one object visible in the image that is outside the solar system. I think this should be easy. Just look at the image. Outside the solar system that can be seen on this image.
Galaxies? Undiscovered galaxies?
Galaxies is a galaxy is a possible answer. A more obvious answer though would be, always go for the obvious answer here. These are more likely to be what?
What was August?
Stars, right? A galaxy and a star are different things. So I would say the better answer here is a star. Okay. I'll put galaxy here, but I'll note not so galaxy, but not an obvious answer. As instructions say, visible, right?
Does the mark scheme allow galaxy as an answer?
Mm-hmm. I won't. I'm just gonna say it's not a safe answer. So I'll change that. Not a safe answer. Okay.
Fine.
All right. Okay. It could be given, but I'm not so sure. Another possible answer here, even could be planets, because at the moment we don't know if some of those dots are actually planets, but they could be seen. Okay. All right. Next. Okay, this is gonna go into topic 8. Show that the apparent brightness B is proportional to 84 over D, where D is the distance, D is the temperature of the surface of the object, and A is the surface area of the object. This is gonna... Since it's a show, that means you're gonna have to start with... It's just equal to power over area, right? It's the same thing. So this is gonna be equal to power. This equal to power. I'll just say power, right? And this power is what now? We can take this from unit 8. Or from topic 8.
Power is emissivity, Boltzmann constant, area, temperature, power 4.
Okay, there. So you put that in, right?
Well, what happened to the area? What happened to the area?
Well, that's still okay, because if you think about it, the area of a star is more or less constant. The area of an object in this case. The surface area of the object is more or less constant, right?
Oh, yeah. Okay.
So this is going to be emissivity sigma area. Actually, no, you don't even need to do that. Area T to the 4 all over 4 pi D squared. These are all constants, right?
And you don't need constants in a proportionality.
Exactly. So this means B is proportional to A T to the 4 all over D squared. Okay. So... Okay, you started off right, but I think you got lost with converting what means what, right?
Now I got it.
Okay.
I just didn't know that before.
Okay, so this is a use... I'll just highlight that. That's going to be a really useful idea, okay? So the power corresponds to luminosity, and the intensity corresponds to brightness. Okay?
Yeah, okay. Luminosity and power are the same. Intensity and brightness are the same.
Yes. Okay?
Fine.
Alright. Okay, let's move on. Part B. Two of the brightest objects in the night sky are the planet Venus and the star Sirius. Explain why this equation, the equation B is proportional to 84 over D squared, is applicable to Sirius but not to Venus. Okay, let's go back to the problem. Oh, okay, never mind. Tell me if you need help.
Venus doesn't have brightness, right?
It does. It actually does. If you look at it from Earth, it's actually the brightest. No, second. No, third. It's the third brightest thing you'll see in the sky. The sun's the first, the moon's the second. Venus will be the third. Okay. Sirius would be fourth. No. Yeah, fourth. It would be the brightest star, but it would be like the fourth or fifth brightest object. Okay, but either way, why will this equation apply to Sirius but not to Venus? Okay, I'll give you a clue. Go back to Unit 8. This equation is essentially the black body equation, right?
Black body.
And what is this? This is the intensity of the radiation being emitted by the surface. Emitted is the key word here. Venus, does it emit or does it reflect? It's a planet, right? Venus is a planet.
Oh, it does. Does it reflect?
It doesn't reflect it doesn't emit its own light. It reflects light. Specifically, it reflects the sun's light.
And Sirius doesn't?
Sirius is a star. It says so right there, right? So meaning, what does this mean?
So it's what? It produces its own light?
Yeah, it produces its own light and therefore, what? And therefore, you can use the the apparent brightness equation. Okay. Okay.
Oh, and Venus reflects light from the sun.
So it doesn't really. It's visible because it reflects light. So it's not about this anymore.
It doesn't make
Okay.
its own light.
Right. So again, the key idea here. Let's just put that up. The equation applies to a black body emitting its own radiation, right? Venus does not. Venus is visible because it reflects light. From the sun. That's the answer here. Okay. Okay. Next. Okay. The light from a distant galaxy shows that Z is equal to 0.11. Calculate the size of the universe when the light was emitted to the size of the universe at present. Okay, you need to use a formula from the data booklet here. So go to the options.
What was the question?
Okay, here. We're here in number 21.
The light from a distinct. Calculate the ratio size of the universe. I don't know which one to use.
Okay, so let me just
Light from a distant galaxy.
You're gonna need to open up the data booklet here, as I mentioned earlier, right?
Yeah, I have it open.
Okay, physics data booklet. Let me open my copy as well. Okay. Okay, options D. Okay, so Z is equal to you have two possible equations to use for Z.
Do we have if we don't have a cosmic scale factor, then we use the first one. So redshift of a star / galaxy moving away from us.
Yeah. So here are the two relevant equations. So which equation would be more useful here? And z is
The
equal
first one.
the first one. Are you sure?
Yeah.
Okay. Okay. It's actually not the first one, it's the second one.
Well,
Okay.
we don't have a cosmic scale factor.
Well, we kind of do. Our cosmic scale factor is this, right? Okay, and then we're not
No, that's the redshift.
sorry. Yeah, that's the
That's
redshift.
the redshift.
Okay, but our cosmic scale factor here, this one, you're talking about this one, right? Well, here's the thing.
Yeah.
That's that. Somehow. Okay. The idea here. Okay, so this is how you will apply this. Okay, so what you will do now is z is equal to a 0.11, and that's equal to the side. This r here is okay, let's just put r over r0 first, minus 1. So this means that r over r0 should be equal to 1.11, right? Now, what's gonna be bigger? What's gonna be bigger between these two? What's gonna be bigger between these two? Present, right?
R should be. Wait.
Which one is bigger? So this will be r. This will be r0.
R.
So
R0 should be bigger, no?
yeah. Okay. When you think about it, it's because we know that the universe is expanding, right? Because the universe is expanding, then that means the present size should be bigger than the past size.
So R should be bigger.
R should be bigger. So in this case, we're gonna get
Okay, but how does that help us?
Well, how does that help us? We need the opposite. We need r0 over r according to this, right? So what did we do? We just flipped that over. So we also flipped that one over. Done.
And that's the answer?
That's the answer. What's 1 over 1.11? Now let's just try that one.
So the cosmic scale factor is the size of the universe at present?
As compared to some time in the past. This is gonna give us 0.900. 01, okay? So in other words, that ratio is going to be 90% of the universe at this time when the light was emitted was 90% of the size now. Okay. So that's what this equation actually means. This r is like the radius of the distance of that object, in this case our galaxy, to the Earth. Okay. So yeah, we don't need to know the values, we just need to know that ratio at this point. Okay.
Okay.
All right. So let's carry on.
And when will I use the first equation though?
You will use the first equation if you're given a redshift. Okay.
Oh, okay.
So okay, you use this equation here. You use this equation here when you have redshift problems. Okay. Okay. Any other questions?
No.
All right, let's move on then. Okay, next. Outline how Hubble's law is related to Z. What is Hubble's law?
Hubble. I know Hubble's formula.
Uh-huh. Yeah, that would be Hubble's law.
So H is equal to relative velocity of light divided by distance from Earth.
Okay. So how is this related to Z?
I don't know.
Okay. Okay, the idea here is that let me just double check this. Okay, hold on, let me check the mark scheme. I'm suddenly lost. Okay. Where are you? Here. Okay, so if we check the marking scheme here, let me just read it out first and then I'll explain further. Okay. And it's loading. Okay, hold on. I cannot access the marking scheme all of a sudden. Just give me a moment. Okay, so while I'm trying to load this, your mocks you said will be on this Friday, if I recall right. Is that correct?
I have paper 3 on
I see.
Wednesday.
Paper 3 is on Wednesday. Ah, that's why you're studying this first. Okay. I see. Okay, let me just get the marking scheme up. Yep. Okay. Okay, here we go. It's open. This is section D. Ah, this is... Oh, that's paper 1. Here. Okay, got it. So let me just read the marking scheme quick just to be sure what the answer is. Okay. Okay, so the idea here is you have to go back to Hubble's law. Okay, let me just post the actual marking scheme answer here. Okay, so here's what the marking scheme says. What does this mean? Okay, it's still loading. Okay, so the Hubble's law is a measure of the recessional speed, which is Z, right? Redshift. Okay. Redshift is proportional to the distance from the Earth. Okay, or it combines the two equations here into one expression here. Basically, how would I explain this given this marking scheme? I would say it like this. Okay. Hubble's law is states. I'll just say states. Hubble's law basically states that the farther an object is from the Earth, the faster it is moving away from us. Okay, I think this will be okay, the speed is shown can be determined from the redshifts of said object. There. So yeah, I think this is a good enough answer if I would write one myself. Okay? That the farther, not farther an object is from the Earth, the faster it is moving away from us. The speed can be determined by... Okay, that's it. And I'll just add proportional. Not enough space. Okay. Hubble's law. Or I'll just probably just do this. The farther an object is from the Earth, the faster it is moving away from us. And the speed can be determined by said object, which is proportional to the distance. That's it. Okay, I think that's the best way I can say this. Okay. So Z is the redshift. Which goes into here. Okay. All right. Okay. Okay. If you haven't noticed, a lot of these things in astrophysics, it's just memorizing stuff. Right? Once you memorize this, the formulas become pretty straightforward. Okay? All right. So let's move on. C. Hubble originally linked galactic redshift to a Doppler effect arising from galactic recession. However, Hubble's law is now regarded as being due to the cosmological redshift, not the Doppler effect. Explain the observed galactic redshift in cosmological terms. Oh, okay. So in other words, we have to look into, when we say cosmology, we're looking into the origins of the universe. So why do we have this redshift from the origins of the universe?
Because does it have to do with the galaxy expanding?
Not the galaxy, but yes.
And that the wavelengths are getting longer?
Yes, exactly. But the word here is not galaxy. The word here is universe. The universe is expanding. Okay. Okay. Expansion of the universe. That's only one mark though. The second mark is the wavelength stretch. The wavelength stretches along with it, right? So that's the second mark. The third mark is something that happens in between what you said.
What happened?
Okay, the expansion, it stretches the universe itself. The expansion of the universe stretches space-time in more technical language. In slightly easier language, it just makes it increases the distance between objects. I don't like that term though because it's not entirely accurate. Saying it stretches space-time would be better. Okay. So what do I mean? So basically, the universe is expanding, which stretches space-time. Okay. By the way, space-time is a single word like that. This causes the wavelengths of light, to stretch as well, causing cosmological redshift, causing it to shift to the red end of the spectrum. Okay, that's it. Okay, you but that's not bad. 2 out of 3 is not bad. Okay. Do you understand what space-time actually means? Or have you heard about this? I think if
Is
not...
it is it like those grid lines?
Okay, it's something like that. Yeah, you've probably seen something like that. You know, with gravity demonstrations, right? About space-time. Now, the idea first of space-time, just so we're clear, I'll just do this as simply as possible. But the idea of space-time is that it combines space and time into one entity. When we say space, we normally say three dimensions: length, width, and height, right? Okay. Space-time is simply saying that we add time to those three dimensions. So instead of treating time separately, you're treating time as just another dimension. Okay? So space and time put together become space-time. What happens during the expansion of the universe? It stretches space and time at the space and time together. Okay? It doesn't just stretch space. It stretches time as well. Kind of mind-boggling, but that's the idea. But think about it. If you stretch time, that means you lengthen the time. You make the frequency also smaller. Smaller frequency shifts it to red as well. So not only do you stretch the space, you're stretching the time. So you make the wavelength, the whole wavelength thing, actually longer. Okay?
Okay.
Alright. Okay, next. Let's go to the next problem. Okay, this is now number 22. Oh, okay. This is now calculations for number 22. Okay. So Ryan, while I'm pasting this onto the Jamboard, on the next meeting, I see we're meeting again on Tuesday. We'll just do crash course on Tuesday for anything you don't know. Okay?
Okay, yeah.
Alright, so 22. We have this data given. L0 is the luminosity of the sun, and M0 or M dat is the mass of the sun. Show by calculation that eta Aquilae A is not in the main sequence. Okay, which formula do you use?
The first one, I think.
Hey, where did I put my formula sheet? Here. Okay.
Parallax. We have a parallax angle.
Mm-hmm.
Does that mean we
Actually,
use
no, you don't. I'm gonna show the equation you need here. This is in topic D2. Oops. Topic D2. This is the formula you will need. Okay. What does this mean? This formula simply means if this formula is met, if this proportionality is met, the star is in the main sequence. That's it. That's what this formula means. Okay.
So we have to check. So
And-
we have to calculate, saying that's not proportional.
So in our case, the sun and the luminosity of the sun, the mass of the sun and the luminosity of the sun should be proportional to this, right? So, what you need to do is check whether the luminosity and the mass follow this relationship. In other words, you can do this. L over L of eta Aquila A, I'm just gonna say EAA, should be equal to mass of the sun divided, not theta, mass of the sun divided by the mass of eta Aquilae A. Is it 3.5? Like that. Okay. If this happens, if this is true, if true, eta Aquilae A is main sequence. So that's all you have to check. Okay.
And now we can substitute.
Yes, we can just substitute.
So it's just gonna be 2630 divided by an unknown number equals
Well, it's not that you don't.
5.7 divided by an unknown number.
Okay, but remember that unknown number is actually in the proportion in those numbers as well, because you have L0 M0 here, or M sun L sun, right? We'll read that as L sun and M sun, right? So
Yeah.
okay, so what do? Is we get L sun over 2630 L sun, right? So that cancels out. Is that equal to, I'll just put a question mark, is that equal to mass of the sun raised to 3.5, okay, divided by mass of eta Aquilae A is 5.7 M sun. So that cancels out as well. So from here, it's pretty obvious, but you really need to still check. But it's pretty obvious it's not. 5 times, that's basically 6 times 6 times 6. More or less. Right? Okay. So
So then after you keep solving it, it's not gonna they're not gonna equal each other.
if they're not gonna equate to each other, so not main sequence. Okay. Also, another important thing to note here is that the sun is main sequence.
Oh yeah.
Okay.
Okay.
So it's okay. So basically that's the idea here. If the star is in the main sequence, we have this proportionality. Okay.
Okay.
All right. Show by calculation. All right, next. B. Yeah, we need to, I think I need to give you another paper for review later. Yeah? You try to answer it on your own.
Yeah.
All right. Okay. Okay, here in B, you're right now, you're going to use the estimate in parsecs the distance to EAA using the parallax angle in the table and using the luminosity in the table given this. Okay, so there are two things you need to calculate. The distance in parsecs in two methods. Okay, I think you'll need the data. I'll copy the data again. Okay. Okay, so which formulas do you need here? You'll need the first formula. Okay, how about the second one?
What was the question saying? It's like, but I can't read it.
Okay, all right, let's make it bigger so you can read it.
You have to move it to the right.
To the right.
Question.
Okay, there.
Okay, using the luminosity in the table, given that L. Okay, what's the question asking?
You're looking for the distance to eta Aquilae A. First is you need to use the parallax angle in the table. Okay.
For that question, yeah, you do 1 over
Okay.
the parallax angle,
Correct.
and then don't you just get the distance?
Okay, correct. So this part is correct. You use this formula. which is gonna be pretty straightforward, right? Okay.
Yeah.
Okay. How about the second one? Luminosity of the given using this luminosity here, given that L sun is this. Okay. You're looking for
Oh, we use isn't that like the Cepheid variable?
no, we don't.
Um.
It's not the Cepheid variable thing. Okay, I'll give you a hint. You're given the apparent brightness and you're given the luminosity, right? So what's the relationship between luminosity and brightness? We just actually we did this earlier, right?
Yeah, you do B equals L over 4 pi D squared.
Correct. So you use this.
And then you just solve for D.
That's correct. Okay. So of course, that means if everything matches, then these numbers should be close to each other, right? Okay.
Yeah.
All right. But of course, I'm thinking that they won't be. Okay, because in C, that's the question. Why are they different?
Why is it different?
Okay, first of all, can you solve this next those two parts first? Okay, where is the
Is this right? 0.0004? Or wait. 1, 2, 3, 4. 4 times 10 to the power of 4 times 10 to the power of negative 4?
No, that's too small.
I mean, wait, something's wrong.
Maybe you put 3 instead of negative 3.
I mean,
for the exponent of 10.
times 10 to the power of negative 3. Okay, 423.
423. Is that for part 1 or part 2?
For part 1.
Yeah, correct. 423.
0.7.
423 should be fine. Or it's 0.7, so that should round off to 24, right? Parsec. Okay. Okay. How about part 2?
I'll see in a moment. Luminosity. Okay. Divided by 4 pi squared. I got 53,000.
Mm-hmm.
9. No, wait.
53,000.
No, not 53,000. 539,000.
59,000.
146.
146.38.
0.38.
That's way too big.
Yeah.
Okay.
Oh wait, sorry.
I'll give you a hint. The distance you will get here would be in meters, so you have to convert that into parsecs afterwards.
Wait, calculator says no solution found.
Yeah, because it's too big, I think. Right?
Yeah. That's not convenient.
Okay. So the idea here is you have to look for... once you find your distance, you'll get a certain number, right? And you have to divide that number. You have to convert that distance into parsecs. And there's a conversion factor in the data booklet. Okay. So what do we do here? We get the square root of L over 4 pi D. 4 pi B, right? So that's all you need to plug in.
Yeah.
Okay. Your L, you're gonna have to do that as 2,630 times this. That's the L, right? 20630.
Oh, I need to multiply those two L's together?
Yes. Because this L here is the luminosity of Eta Aquilae A. This L here is the luminosity of the sun. You have to put this value in here. Okay. Times 3.83 times 10 to the 26. Oh, I will not forget that square root. Should be there. 26. So what do we do on the bottom? You still have 4 pi. Right? And your B is given. Your B here is given as times 7.20 times 10 to the minus 10 watts per meter squared. Okay, well, let's not put the unit in anymore. So that's the idea. Once you take the square root, that's your distance in meters. Okay, so I'll just calculate that right here. So 2630 times 3.83 exponent positive 26 divided by 4 divided by pi divided by 7.2 exponent 10 negative 10 equals. Okay, and then we let's just take the square root. This is gonna give us in the calculator, this is gonna give us 10 point, oh, that's a big number, so let me see. 10.6 times 10, let's see, 3, 6, 9, 12, 15, 18. It's 18 meters. Okay, or properly done, that's going to be 1.06 times 10 to the 19 meters, right?
Yeah.
Okay, now you have to convert this to parsecs. There's a conversion factor in the data booklet.
This is in meters?
Yeah, that answers in meters. You have to convert that to parsecs.
So you get 341,000? No, wait, 3.4 million or something like that. 3419443 parsecs.
There. 1 parsec is 3.26 light years. Or, yeah. Which is gonna be this. So, I'll just copy this from the booklet. This information is on page 3. Okay, so you can use these two conversion factors to first you convert meters to light years, then convert light years to meters per parsec. Bless you.
Thank you.
All right, so that's the idea. Once you get your answer in meters, convert. Okay, so convert to light years by using this, and use this to convert to parsec. Okay, I'll just tell you the answer straight away now. This is gonna be 324 parsecs. No, not 324. That's 342.
And the other one was
342. But either way, it's different, right?
yeah.
Okay. Why are they different? I'll give you the most simple answer. Well, I'll show you something that should tell you the most simple answer. Look at that angle.
What about the angle?
It's tiny. Think about it. The arc second itself is already tiny. Then you go for 10 to the minus 3. It's absolutely minuscule. Right? So small angles mean it's hard to measure, meaning it's prone to what?
Error.
Prone to error. Okay? So that's one possible answer in the marking scheme as I'm looking at it now, but that's the answer I would go with. Okay? The parallax angle is so small. That it is prone to measurement errors. That's it. Okay? So that would mean that the parallax method would be more likely the incorrect one. Okay? Okay. Okay. Okay.
But that's only 1 point.
That's only 1 point, right? Now another point here, the question was again are different, okay? But the thing is, another thing here is that you have to, that's the comment on that one. The other comment here is the apparent brightness. So you have to kind of go back to this as well. Right? Okay. Okay. Oh, okay. I think I'll tell you a quick story before we answer this. Do you know that in space right now, orbiting the Earth, I think, there's a sphere made of aluminum. And it's one of the most important instruments we have right now in terms of astronomy. It's there because we basically need to calibrate our instruments. I literally found out about this literally last night. Okay. Okay. Why
what
am I?
does the ball do again?
That ball of aluminum in the in outer space is used. Well, we basically point our instruments to it first to calibrate. Well, to calibrate it, because the aluminum sphere is designed so that we know how far it is, and we know its dimensions, that we know how the instrument should react to it, and that's what we use to calibrate it. Okay, so in other words, our instruments still need calibration. These values here, the luminosities, the brightnesses, the parallax angles, these all of them need to be measured, right? So
are they all estimates?
all the quantities, which is L, B, and parallax angle, right, need to be measured. So what which exposes everything further to systematic and random errors, right? That's it. Okay, so that's the second mark. There's a third mark on the marking scheme as I'm reading it. You can say that, yeah, They may be different, but they're the same order of magnitude according to the marking scheme. Yeah. So the answers are not significantly different though. Answers are not too different as they are still within the same what's this? Order of magnitude. From MS. Okay. Personally, I wouldn't come up with this third answer. Even though it's in the marking scheme. I'd probably be answering these first two. Okay. All right.
Okay.
Okay. Okay. I'll just okay, and then let's go to the next one. Next problem here is it's a Cepheid variable. Cepheid variable. So explain why the brightness of eta Aquilae varies.
A specified variable.
Mm-hmm.
We know it's period.
Mm-hmm.
But that doesn't matter.
Okay, it's not about the period, but that's gonna be important later on. But the question is still about the brightness. Okay. So, what are the key ideas again?
It has a constant brightness variation.
Okay, I'm gonna look at the mark scheme here, see how many marks you'll say. Okay.
A specified variable has a varying brightness variation, but the brightness is always gonna be the same.
No, not quite. Well, you got 1 mark, just so you know.
Depending on the period.
Yeah, they got 1 mark, depending on the period. In other words, yeah, that's your mark, depending on the period, right? Okay, again, what's the key idea in Cepheid variables? Let's put an image here for you to help remember. Okay. Where's that image that we have? Okay, this is gonna work. Okay, again, use this diagram to help you with your answer. When does it become bright and when does it become
at its maximum?
Yeah, but why does it become
at the maximum?
Okay, why is there a maximum brightness? What's happening there? Look here. This part. What's happening here? It goes from small to large,
big,
then back to small, back to big, right? And so on. So what's changing here?
The intensity.
Okay, right.
The brightness.
Okay, but okay. Yeah, the brightness changes, but why? Okay, I think I'll just tell you now, okay? How do you get your 3 marks?
Because of the period.
The period is 1 mark. You need 3 things, right? Don't worry, I'll tell you now. I'll tell you, okay? 1, the period, okay? The variable changes brightness, right? Because its diameter changes, varies with time. Okay, the second part is the variation. The variation happens with a constant, with a predictable period. This is how I would say it again. Yeah. Okay. So that's the first part. The second part, we got 2 marks already, right? Okay. The variation happens with a predictable period. And then what's the third mark I will say? I'll say something along the lines of, as the size of the star changes, two things happen. Okay, first is its brightness changes. Okay. So not the brightness. Its temperature changes. So temperature changes. And then the second one is the amount of light that can pass from the core to the surface changes as well. I'm just going to put here larger equals more light equals brighter. Okay. And then temperature changes. So what happens? Hotter equals brighter. That's it. So this is how I would say my answer. Something like this. But I think I will not even mention 2. I will probably just mention 1 and 3. I'll just put that in bracket. Okay.
The variable changes brightness because its diameter varies with time. So because the period changes. And then you would say that the temperature changes and the amount of light that passes from the core to the surface changes. How come the light changes?
Okay, this is, I was expecting you to ask this. Okay, the idea here is this: when the star is small, it's dense, right?
Yeah.
Dense means atoms are closer together, or let's say hydrogen is closer together, right? H close together. So what happens? Basically, if that's the hydrogen, very dense, the light is gonna... I'm gonna use a different color here. I'm gonna use blue. Okay. So the light is gonna go like that, gonna bounce off, bounce off, bounce off, bounce off, like that. Right? It has a hard time escaping. Right? Now, when it's large, it's not so dense. So what happens when it's not dense? The hydrogen will be not so dense. Okay. So what's gonna happen? The atoms are further apart. Like that. So any light coming from the core will have an easier time passing through. Some of them still end up bouncing off, right? But bouncing off fewer times. In other words, the bigger it is, the more transparent it becomes.
The bigger it is,
okay,
the more transparent it becomes.
Yeah, larger means outer layers become transparent. And therefore, more light and therefore brighter. Okay. Okay. Okay, let's finish. I think this is gonna be the last. We still have I still have a few questions here. So eta Aquila A was on the main sequence before it became a variable. Compare without calculation the time eta Aquila A spent on main sequence to the total time the sun is going to spend on the main sequence. So in other words, the question here is which star has or will spend more time in the main sequence? Without calculation, right?
To the total time?
basically the idea here is all stars basically start off at main sequence, right?
Yeah.
All stars start off at main sequence, and then eventually they become giants. And then what happens after giants depends on the mass, right? So that should give you a hint already. That should give you a hint. Which stars become giants much faster? Massive or light, or heavy or light stars?
Super giants or just giants?
Just giants. Which ones become giants faster? Heavy stars
Bigger
or light stars? Bigger stars, right?
Yeah.
Okay. So, without calculation, out of the two, between the Sun and Eta Aquilae A, which one spent more time in the main sequence?
The Sun.
The Sun will spend more time in the main sequence. Reason being?
Because it's not in, because the star, I mean the red giant is not in the main sequence.
Okay. There are three possible reasons for it, just so you know, okay? All of them relate to the same basic idea. I'll just put the mark scheme here. Okay, the first one, as you said, is... Okay, Eta Aquilae A will be shorter. I will spend less time in... for Eta Aquilae A. Okay. The reason being, it's already... this is the one I would say. It's more massive. And therefore, mass is related... actually, no. This is what I would say, personally. And I think this is gonna be the more common answer. Okay. More massive stars spend less time in the main sequence. Okay. Star more massive. So, up in mass means down in time in main sequence. Okay. Now, another possible answer here, this one, even though this is correct, I don't expect a lot of students to answer this one. Okay. Or this third one as well, even though this is correct. Okay. However, for those who are interested in the HR diagram, if you're interested in the HR diagram, you'll see that Eta Aquilae A is to the left and higher up. So it's more massive. Okay. All right. So again, personally, I'd go for the second one.
Okay. But you need to mention 2 points anyway.
The 2 points are shorter. This is the second point. That's 1. Then this is 2.
All right.
Okay. All right. All right. I think that's the end on that particular sequence. We are now on number 23. Interesting. 2017, which is about 5 years ago. It's been 5 years. Okay. 2 neutron stars were observed to merge, forming a black hole. The material released included chemical elements produced by the R process of neutron capture. Describe 2 characteristics in R process. Produced by the R process. Okay. 2 characteristics.
I remember we mentioned this.
Yep, that's right. We did. Let's see if you can recall something about it.
A rapid nucleon capture process.
Exactly. R stands for rapid.
But I forgot what happens in it.
So again, the idea here, okay, the key idea here is that neutrons are being absorbed, and at the same time, nuclei are decaying via beta decay. That's the key idea. Okay, beta decay is happening, neutron capture is happening. Which one's gonna be faster?
Which is happening?
Again, there are 2 things. We have neutron capture, rapid neutron capture. That's the first thing happening, right? And the second thing happening is beta decay. both in the neutrons and in nuclei. Okay, neutrons actually are unstable, so if they're outside of a nucleus, they have a tendency to decay via beta decay. Okay, so out of these two processes, which one would be faster?
Is it the rapid neutron capture?
Okay, this is faster. Meaning what?
I don't know. Oh, it builds up heavier elements.
Okay, so because this is the faster process, elements can be built faster than they can decay, right? Yeah. So elements can be formed faster than elements decaying. Yeah, that's it. Okay, there's actually a third point to it. Okay, there's a third point to it, and I'll just mention this because this is in the marking scheme. The third point, which you don't need to get the marks here, is that this happens, this process. So our process happens for elements with heavier, I'll just say heavier than iron. Okay, this is an important point here. The R process happens for elements heavier than iron. Properly speaking, I'll change the word heavier. No, I'll just put that in bracket. With higher atomic number. Okay. So again, this third point is important because the R process cannot happen for elements that are lighter than iron. Okay, it has to happen for elements heavier than iron. Okay. All right. So correct, you got your 2 points there because you said rapid neutron capture earlier, right? Oh, sorry, you get 1 mark. Okay. Okay, next, number 24, the last one for this problem. Okay, cosmic microwave background radiation. We've talked about this on our last lesson, I guess, right?
I remember. But I've never seen that word before.
Which word? Anisotropies. Correct?
Yeah.
Okay. Okay. We actually have discussed this, but I'm pretty sure you don't remember this word. It looks weird.
Yeah.
Okay. Let's discuss this further. Let's discuss this word again. Okay. So I'm going to separate this into the two things to make it easier to understand. Anisotropy. I'm gonna use the singular form isotropy. An means not, right? Isotropy means symmetric. Symmetry. Well, it's not exact symmetry like math symmetry, but basically, we can say another word here, or evenness. This is a better word. Evenness. When something is isotropic, it means it's really even all throughout. Okay? So anisotropies means there are unevennesses in the cosmic microwave background radiation. Okay? So that's what it means. So state the nature of this anisotropies.
Well, wherever you point the at any point in the universe, you will have the same static sound.
Okay, that's the proof of it. That's a proof of it, right? Okay. Hold on. How do I say this? How can I say it in a different manner? Okay. Now think, if you think about this, where did the cosmic microwave background radiation come from?
The explosion
This is from the
on
Big
the.
Bang, right? Exactly. This is the back. This is the black body radiation of the universe. Radiation of the universe during at the Big Bang. Okay. In other words, this another way of saying this now is, this means that this cosmic microwave background is a measure, or is an indication of the temperature of the universe during the Big Bang. Okay. During the Big Bang. Okay. So this should be enough of a clue for the moment to help you answer the question. So what do these okay, if it's completely even, if there were no anisotropies, okay, then what does that mean? That means that the temperature of the universe at the Big Bang was even all throughout, right? But the fact is, there are anisotropies, meaning what? Is meaning the temperature of the universe during the Big Bang was
the same.
If it's isotropic, right?
Yeah.
If we just look at this term, it should be the same, right? But because of the word anisotropies, because of the prefix an, it means
Now
it's not even. Meaning, let's just put this here now. Anisotropies.
The universe varies in temperature.
Yeah, anisotropies indicate temperature differences, right? Within the universe during the Big Bang. Okay, so that's what it is. Now, what could have caused those different, the temperature differences? The
cooling of the universe.
Okay. I wouldn't say the cooling, because if you think about it, the universe contains all the energy it's in itself already. It cannot get out of the universe, right? So the cooling is due to a different factor. Okay. Now think about it this way. Let's think about this in terms of the modern universe. Where would you expect the hot regions to be? In galaxies or in deep space? Galaxies would be hotter than deep space, right? Because it has more mass. So, yeah. What does this mean? The temperature differences indicate what? The uneven distribution of what? Mass in the early universe. Okay, that's what this means. So, this is the whole idea. Let's go back to the question. State the nature of the anisotropies observed in the cosmic microwave background radiation. Okay, so the nature is that, let's go back to the word anisotropy. Meaning, the CMB, well, just CMBR. Some books abbreviate this further to CMBR. Okay, CMBR is uneven, so therefore what?
So therefore temperature differences.
Correct. And since it's only one mark, we go straight to that answer. It's this. This goes here. Okay. All right, so I'll just type that in. CMBR. Okay. Just type that in. CMBR. Anisotropy. Entropies mean it um okay, but remember that because of the fact that the CMBR, the anisotropies are really tiny, it's really still quite even. Okay, at least to the way we look at it, it really requires these small indicate temperature differences within the formation of the universe. Okay. Or within the universe. I'll just say within the universe. It doesn't have to be the formation. Okay. This is good enough as an answer for here. Okay. Second part, identify two possible causes. So we have one right here in the discussion I've made, right? Okay, the uneven distribution of mass is one of them. Basically, you can just say density fluctuations in a more technical sense, right? So you can say density fluctuations. Fluctuations. Okay, what are other two possible causes? Okay, the more reasonable one, okay? The more reasonable one is, well, I'm gonna ask you something real quick just to help you remember this, okay? You've learned about antimatter, right? Back in Unit 8. Back in Unit 8. Okay, what is it?
Matter that exists, but you can't prove it.
Okay, antimatter, to be more specific, is the equivalent particle of a matter particle with the exact same mass, but every other property would be opposite. So for example, the charge would be positive, then the antimatter would be a negatively charged particle. So the proton is positive, the antiproton is negative, something like that, right? Okay, now if you think one thing about antimatter and matter is what happens when you put the pair together, the matter antimatter pair, they annihilate, they destroy each other, it creates energy, right? So if you think about it from the other way, when you have a lot of energy, you should be able to create a matter antimatter pair, right? So if you think about it further, then that means there should be about the same amount of matter and antimatter in the universe, right? There should be about the same amount. But the fact is, if there is about the same amount, then where's the antimatter? All we see in the universe is matter, right? Okay, it's a long story. We don't know the exact answer to that, but one idea that's gonna be useful here is what's called quantum fluctuations as well. Okay. Now, it doesn't really go all the way to matter antimatter only. There are other possible ways that this can happen. But basically, during the early universe, because the universe was small then, right? So these quantum fluctuations, basically, they made these quantum fluctuations are what make the unevenness of the cosmic background radiation. It adds to it, okay? So these added to the cosmic microwave background radiation in the early universe. Okay? And what happens with the expansion of the universe, these fluctuations became bigger. the fluctuations became bigger. Okay, so this is another possible source of the anisotropies in the cosmic background radiation. Okay. During the beginning of the universe, these quantum fluctuations, even though it added to the CMBR, at that time it wasn't really a big addition. It was more on these temperature differences at the time. But as the universe expanded further and further, making everything bigger, this made these fluctuations bigger as well, until they became noticeable in the CMBR. Okay, so these are the two. There's a third one in the marking scheme. I'll just tell you what the third one is. It's more on dipole distortion due to the motion of the Earth. In other words, the motion of the Earth actually contributes to this CMBR as well. Well, at least the way we observe it. But I will not normally say this one. For one reason, it's not really a big cost. Okay, these two are gonna be the better answers.
Quantum fluctuation.
And uneven distribution of mass in the early universe.
Yeah.
Okay. All right. So that's it. So is that the last question here? Yeah, that's the last question from that paper. Okay. All right. So Ryan, let's take a quick break, maybe 3 minutes, and then then we can continue with another paper. I'll look for an earlier paper. Yeah.
Okay.
All right. 3-minute break for you. I know you need it.
Okay. My brain.
All right. All right. Uh, let's see now. Okay, Ryan. Okay, I think we're ready to start. Are you there yet?
Yeah, yeah.